Okay, we're going to look at section 10.4, which involves solving equations with logarithms and exponentials and their applications. Okay, so the first one, we've actually already looked at problems like this. I have only one logarithmic expression, and to solve that, I'm going to rewrite that in exponential form. Since there's no number there, I know the base is 10, so this becomes 10 squared is equal to x plus 3. So that becomes 100 equals x plus 3, so x equals 97. The second one, I have logs on one side of the equation. What I'm going to do is use either the product rule, the quotient rule, the power rule to condense that so I can rewrite that in exponential form. This will become log base 2 of x plus 3 times x minus 3 equals 4. So log base 2 of x squared minus 9 equals 4. Now rewrite that in exponential form. So 2 to the 4th is equal to x squared minus 9. So 16 equals x squared minus 9. X squared equals 25. So look at both of those answers. If you put negative 5 in, you'll have log base 2 of negative 2. You can't have a negative result. So therefore, x is equal to 5 only. For C, I have log expressions on both sides of the equal sign. So again, I'm going to use the product rule, quotient rule, or power rule to condense this. Then I'm going to use the one-to-one property. So this becomes log x times x minus 1 is equal to log 8x minus 12 over 2. So on the left, I have x squared minus x. On the right, I have 4x minus 6. So this becomes x squared minus 5x plus 6 equals 0, and that factors to x minus 2, x minus 3 equals 0. So x is equal to 2 or 3 for C. So using those properties to condense or expand will help you solve some of these. Now, when I want to solve an exponential equation, something like 2 raised to the x equals 10, because what I would normally do is try to get like bases, but I can't do that with a 2 as a base equal to 10. So I'm going to take the log of both sides. So log base 10 of 2 to the x is equal to log base 10 of 10. When I use the power rule, I can bring the x down, so I have x times log base 10 of 2 is equal to log base 10 of 10 is 1. So now, using my calculator, I can find that log of base 2 is equal to 0.301. So I have 0.301x is equal to 1. So x is equal to 3.322. We'll just go to 3 decimal places on that. So when I have an exponential equation, and I'm not sure, I can't get those bases to be alike, I can actually take the log of both sides. Letter E, I have 2 raised to the x raised to the 2, and then 4 raised to the 3x minus 4. I can get these bases the same. We've already looked at equations like this. So I have 2, power to a power is multiplication. This becomes 2x is equal to then 2 raised to the 2, power to a power, this becomes 6x minus 8. So I get 2x is equal to 6x minus 8. And then minus 4x equals minus 8. So x is equal to 2 for E. Okay, for F, again, I have 2 raised to the x minus 1 is equal to 3 raised to the x. and I can't get those bases to like, so I'm going to take log base 10 of both sides. So I have log base 10 of 2 raised to the x minus 1 is equal to log base 10 of 3 raised to the x. Then go ahead and use your power rule. So I have x minus 1 times log base 10 of 2 is equal to x times log base 10 of 3. Now in your calculator, you can find log base 10 of 2, which we already actually found not too long ago, x minus 1 times 0.301. Remember, you're getting this value in your calculator. And then log base 3 is going to be 0.477. So now I have 0.301 x minus 0.301 is equal to 0.477x. I'm going to subtract 0.301x from both sides. And I will have minus 0.301 is equal to, let's see, 0.477 minus 0.176x. So take then negative 0.301 divided by 0.176, and you're going to get x is equal to negative 1.71. Okay, so if you have bases in an exponential equation that are not the same and you can't get them to be the same, you can take the log of both sides. There's also the change of base formula, which we talked about briefly with that one problem. If a and b are positive numbers not equal to 1 and m is positive, then the change of base formula becomes log base b of m divided by log base a b of a. So in your calculator, if you had something like log base 6 of 9, you would use your calculator and base 10 and make this log base 10 of 9 divided by log base 10 of 6. And that's how you could find 6 raised to what power gives you 9. Okay, so the solving strategy is if the equation has a single logarithm or a single exponential expression, rewrite the expression using the definition y equals log base a of x if and only if a to the y equals x. Number 2, use properties of logarithms to combine logarithms as much as possible. 3, use the one-to-one property. 4, to get an approximate solution of an exponential equation, take the common or the natural log of each side of the equation. Now we have just a few applications problems. And those applications problems, we're going to use just a few equations. For financial, continuously compounded interest is going to be A equals PE to the RT. For scientific notations like bacteria decay or radioactive decay or bacterial growth, something like that, we're going to be using A sub n equals A sub 0 e to the kt. They're actually essentially the same formula, just a little bit different notation. Okay, so let's look at the first problem. It says, if $500 is deposited into an account paying 8% interest compounded continuously, then how long will it take the account to have $1,000 in it? So the 500 is the principal P that I begin with. The 1,000 is what I will have after I find out how long, that's A, how long it takes. 8 is the rate. So now using this formula, A equals PE to the RT, I have, after some length of time, I will have $1,000. I started with 500. Base E raised to the rate, remember 8% is 0.08 times t. Erase that out of the way. So divide both sides. You want to isolate base e. So divide both sides by 500, so you're going to get 2 is equal to e 0.08t. Now when you have your variable in the exponent, this is where logs really are useful. Now how will you solve that? If you take the natural log of both sides, remember the natural log and log base 10, all of the properties are exactly the same. They're just two different bases, the common base 10, or a base of your choosing, and e is ln, and that's the base of the natural log. So take the natural log of both sides. ln of 2 is equal to ln of e to the 0.08t. All the properties are the same, so I'm going to use the power rule to bring 0.08t down in front. So I have ln of 2 is equal to 0.08t ln e. Now, ln e is like saying e raised to what power gives you e? So the natural log of e is 1. So I don't have to worry about that. It's like multiplying by 1. So now I can find t simply by dividing both sides by 0.8. So I have t is equal to, and then in your calculator, you can find ln of 2 divided by 0.08, and you should get approximately 8.66 years for your money to double at 8%. Okay, so when we have e, we're going to use the natural log. Number 2 says the number of grams of a radioactive substance that is present in an old bone after t years is given here. It's like this formula. Only a sub 0 is 8. So where r is the decay, the rate of decay. How many grams of the radio substance were present when the bone was in a living organism at t equals 0? So that means that A is equal to 8e to the r to the 0. So that's e to the 0, which is 8. Now it says if it took 6,300 years for the radioactive substance to decay from 8 grams to 4, then what is the decay rate? So it declined from 8 to 4, e, and it took 6,300 years, so I'm looking for my rate. So again, I'm going to divide both sides by 8, so I can isolate e. So I have 1/2 is equal to ln, sorry, too soon. 1/2 is equal to e to the 6,300 r. Now take the natural log of both sides. So the natural log of 1/2 is equal to the natural log of e to the 6,300. And I had r, but actually I'm going to write that as k. You'll see them interchangeable, the rate as r or as k. Use the power rule. So the natural log of 1/2 is equal to 6,300 k. Natural log of e, again, natural log of e is 1. So now I can divide both sides by 6,300. So the natural log of 1/2 divided by 6,300 gives me that rate k. It's natural log of 0.5 divided by 6,300. Make sure to close your parenthesis when you're using your calculator on that natural log. And that gives me k is equal to negative 0.00011. Okay, because it has to be negative because it's actually going down in value. Okay, homework is here. We'll work on that tomorrow. That's it for the notes. I'll see you tomorrow. Have a good evening.